ولأن برنامج المؤتمر حافل، فهو ما بين الباحث والصناعي والمختبرات، أبحاث الجامعة، السادة هيئة التدريس في الجامعات، وهو يضم كل هذا الطيف الخاص في عالم الألوان والدهانات. يشرفنا تقديم الدكتور أحمد جمعة. I'm honored to introduce Dr. Ahmed Jum'a. He is the General Manager of R&D and Technical Service of Crystal. هو المدير العام للبحث والتطوير والخدمات الفنية لشركة كريستال، ثاني أكبر شركة في العالم لإنتاج مادة ثاني أكسيد التيتانيوم، ليحدثنا عن التقنيات المبتكرة في ثاني أكسيد التيتانيوم للدهانات لتحسين خواص الهواء المحيط. دكتور Ahmed Jum'a has MSc and PhD in Chemical Engineering from University of Bradford, UK, 1987. He worked as a lecturer in University of Bradford, 1987-1990. Research Manager of AkzoNobel, UK, from 1990 to 1994. 1994-1995 Lecturer and Technical College of Riyadh. 1995-2003 Technical Director of SIPCO Paints. 2003 to 2006 General Manager of SIPCO. 2006 to 2009 General Manager of SIPCO and Dyrop. 2009 till present he is the General Manager of R&D and Technical Service of Crystal. Please join me welcoming Dr. Ahmed Jum'a. أهلا وسهلا.
بسم الله الرحمن الرحيم والصلاة والسلام على سيد المرسلين. Gentlemen, Assalamu alaikum and good afternoon. Firstly, I would like to thank Al-Jazeera Paints for the kind invitation to speak in this conference. Secondly, a few words about my employer, Crystal. Crystal is the second largest producer of titanium dioxide in the world. Crystal, in fact, it's unique in the titanium dioxide business. It's a 100% titanium company. We have expanded the supply chain in both directions. In one direction, we have the mining and the slagging and the calcined coke projects. On the other side, we have the titanium metal production and metal fabrication projects. So now to my presentation that concerns with an innovative technology. We call it Crystal Active. Actually, it exploits. This is a nanotechnology that it exploits in terms of titanium dioxide, exploited in paints and in other construction chemicals to help finding some sustainable or helping find sustainable solutions to some of the environmental problems such as air quality. In this presentation, if I know how to, okay. In this presentation, I will cover the following topics: what is photocatalysis, what is photocatalytic titanium dioxide, and some practical applications of this technology, and finally some real-life testing to prove the concept and to prove the benefits. Actually, photochemistry occurs naturally. The most famous reaction that we learned from the school days, the photosynthesis of chlorophyll, and photocatalysis is also a natural process. You need to have three elements. You need to have water in terms of humidity, light, be it sunlight or artificial light, and of course a catalyst. In this case, it's titanium dioxide. The result is the formation of the peroxy and the hydroxy radicals, and these reactive species actually are available to drive the redox reactions to break down the organic species. The titanium dioxide, titanium dioxide photocatalyst offer formulators a multifunctional approach. One in air purification by reducing the nitrogen oxides, sulfur oxides, and VOCs. The nitrogen oxides we refer to NOx, SOx, and VOCs. Deodorization of the air, this mechanism is driven by the photocatalytic reaction degrades the organic matter that actually forming the bad smell. Self-cleaning, also the photocatalytic reaction, it improves the hydrophilicity at the surface, hence a better wetting and leading to a better washability. I know in the kingdom we don't have a lot of rain, but we can with a hose we can actually clean the surface. And finally, the water purification. Titanium dioxide enters into the water membranes, and it has proven a unique advantage in removing some of the special contaminants present in the water. So, just to elaborate a bit more about the mechanism, how this works. As I said before, we need to have three elements. We need to have the light, we need to have the humidity that is present in the air, by the way, nothing special, even in Riyadh it can work. And of course we need the catalyst. Here the harmless SOx, they are converted to sulfates, the harmful, or the less harmful sulfates I should say. The NOx, it's converted to less harmful nitrates, and the VOC, it's converted to less harmful carbon dioxide and water. And here the mold and dirt, it's washed away by the virtue of the improving hydrophilicity at the surface. Some examples of how this technology, or real life examples I should say, this is a paint on a road. You can see one part of the road is treated with the photocatalytic product and the other is not. Is there a pointer here? Yeah, okay. And another example is, again, we said the photocatalytic titanium dioxide destroys the VOCs. The odors are driven by the odors removal is driven by the photocatalytic mechanism through the degradation of the organic material causing the odor. You can see in the kitchens, bathrooms, laundry, and storage rooms. Also, self-cleaning, you can see that treated surface here compared to the untreated one. The treated surface remains attractive for a longer period of time, and hence reducing the cost of maintenance. So, what's really the difference between a pigmentary titanium dioxide and a photocatalytic titanium dioxide? The picture on the left-hand side actually is the standard titanium dioxide. It's actually the pigmentary titanium dioxide. It has a particle size in the region of 150, 170 nanometers to 300 nanometers. This is the sort of particle size range we're talking about. On the right-hand side, the ultra-fine titanium dioxide. This is the particle size range between 50 nanometers and, or in fact, 30 nanometers and 100 nanometers. The special thing about this ultrafine, actually it's made of nanocrystallites, and these nanocrystallites, they are in the size range 5 to 30 nanometers. Okay, this is the small size offers advantages here. Of course, it offers a major prerequisite for a catalyst, which is a large surface area. A catalyst should have a large surface area to provide a good catalytic behavior. And the other thing, the small size actually favors the absorption of light and hence works as a photocatalyst. Some practical applications of the technology. Here we have painted surfaces. In cement and construction materials, these photographs are the courtesy of Ital Cementi. Actually, they were pioneers in using this technology on construction in the construction industry. Another application of the pavements. You can see there's huge surface areas in pavements and that can really use to clean a lot of air. And another or last example is coil-coated architectural aluminum panels that we can see in all the high-rises now and all the sophisticated buildings. This really brings me to the last part of my presentation, real-life testing, how this technology works, what's the evidence. Actually, this is a trial. It's in Camden Borough in London, a wall of an area of 135 square meters. Actually, it was coated with a clear coating, clear photocatalytic, I should say, coating, and it's located in a very high traffic area. Here, this is the wall actually, and there's a monitor. To monitor the NOx, wind speed, wind direction, temperature, and humidity. So, what have we learned from this? By the way, before I move to this, the measurements were taken every 15 minutes, and in all our trials in this technology, there's collaboration with a third party. In this case, it's King's College London. What have we learned from this? By the way, this was run for several years. There are two graphs here. The one on the left-hand side, this is nitrogen oxide. The other one is nitrogen dioxide. To define our axes, for a start, the x-axis is actually the hours of the day, the 24 hours of the day. On the y-axis, the average NOx as measured by the monitor. I should tell you here that each point is an average. For example, let's take a point at number 2 there, that means it's 2 o'clock in the morning. Each point is actually an average of many data points taken at that hour over a period of over 3 months. So here you can see 3 curves. Let's look at the one on the left-hand side. You see 3 curves. The blue one actually the baseline. These are the data before the application of the photocatalytic product. The red line is the data, represents the data after the application of the photocatalytic product. Obviously, there is an obvious reduction in the NOx in this case, and so here there was really another proof. How do you prove this technology works? How do you prove that was not really a coincidence? What we did, we covered this coated wall with the wood panels. We covered it completely, and we measured the effect, and we get the green curve. So we're back to the baseline. This is another proof that the technology works. One more clarification about these measurements. They were taken over this 3 years, I think from August to December, or September to December in this period. So every set of data was taken in the more or less same period of the year. Okay? And another point I would like to highlight here is you can see in the sharp rise in the early hours of the morning and the late hours of the day during the rush hours. Am I doing fine? Okay. Another study that is in, another thing that what we learned from the study is, it's very important to mention this, we could remove something like 0.5 grams per square meter per day of NOx. What does it mean? Let's put it in perspective. That means if we paint a facade over 300 square meters, that can remove the NOx emission from 50 cars traveling at 20 kilometers per day. So this is really a very important sort of correlation here. Another trial was done in Manila. This time it's a train station, and you can understand the pollution around train stations. And this time it was a much larger. The surface area, it was around over 4,000 square meters. and this time also it was real paint. It was a styrene acrylic paint. And obviously there's an obvious obvious reduction of the NOx. And again, what we learned from this, we could remove something like 26 grams per 100 square meter per day. Again, what does it mean? It means like you can remove the NOx emissions from 7,000 cars per day, or if you continue the statistics, it's like something like 300 kilogram per year of NOx removed. So why we choose like photocatalysis? Actually, briefly, because Nauras is saying speed up. Photocatalytic services can dramatically reduce local NOx levels. Photocatalytic coatings are cost effective and easy to apply. They can be applied exactly the same as the convention paints. It's actually the formulator has to work a bit harder on that. To conclude, why we choose photocatalysis? It's actually it's a chance, it's an opportunity to the specifiers, to the manufacturers to offer a way to help the environment, to help a better environment, a friendlier environment. Thank you very much.
Thank you, Doctor. Please, if there is any question to be given to Dr. Ahmed Jum'a of Crystal, إذا في أي سؤال.
Thanks to you. Media is a good that is really dependent on the academic activities. However, we have a lot of academic and can be absorbed or absorbing anything in there, such as the glucoside. Are you going to change the glucoside or the dioxide?
It's actually, you're right, the titanium dioxide is not the only material that can work in this. There are some even also silicate is another one. There are a lot of work to see how we can combine the advantages of titanium dioxide and zinc oxide and even silica as well. So you are right, there are other materials. We're not claiming this is the only one.
Are you present with titanium oxide? Can we transfer the material from absorption from the surface to absorption for all systems? I.e. transform the material from hydrophilic state to hydrophobic state.
Yes.
دكتور شكرا. شكرا للدكتور أحمد جمعة. شكرا دكتور.